The topic of today's video is phase diagrams. You've seen phase diagrams before in the first part of this course on thermodynamics. So the first part of this video is revision. Okay, so a phase diagram relates the state or the phase of a system, so solid, liquid, gas, to the variables that we can apply to that system. In this case here, we're looking at a pressure-temperature phase diagram, which is probably the type you're most familiar with. It contains regions of solid, liquid, and gas, and a couple of important points, the triple point and the critical point, which you should recall from thermodynamics. Now, a phase diagram like this is valid at a fixed or specific constant composition. We need to specify that because composition is another variable in phase diagrams. Here's a phase diagram in which composition varies. It's composition moving from a pure compound A to a pure compound B as a function of pressure. So we see that at low pressures, A and B can mix perfectly as a gas, and at high pressures, they are perfectly miscible, so we get a continuous solution in the liquid phase. And you were introduced to the idea that for thermodynamic reasons, when we're away from pure A and pure B, so in the middle of the solutions, we do not go directly from gas to liquid or vice versa, but we open up a two-phase region in between in which we have a phase separation between the gas and the liquid states. So this is a constant temperature phase diagram. Similarly, we can have a constant pressure phase diagram, which shows composition A to B as a function of temperature. Now we go from liquid at low temperature to gas at high temperature, and again we have a two-phase region. This is the type of phase diagram we deal with most in solid state work, the reason being that solids are not as affected by pressure as gases are. So now we're going to build up a constant pressure phase diagram for solids. So these circles down the bottom of the screen represent the structures of compounds A and B. Now if A and B have the same crystal structures and similar ionic radii, similar electronegativities, then we could probably substitute a purple atom into the green array, like so, or a few green atoms into the purple array, like so. And if they're similar enough, we can do that continuously from green to purple. So we have a continuous solid solution, which we can represent by a formula like this. Now, both A and B have melting points. I'm going to call those TA for pure A and TB for pure B, above which we have a liquid phase, and we can draw a line that connects TA to TB. Although again, for thermodynamic reasons, away from pure A and pure B, we will not get a continuous transition from solid to liquid phases. We will instead open up a two-phase region, which in this case is solid plus liquid. And we can introduce a couple of extra terms here. The lower line we call the solidus in this phase diagram, and the upper line we call the liquidus. This phase diagram tells us what phases will be present for a specific mixture of A and B at a specific temperature. For example, at this point here, I'm in a single phase region of liquid, so I will have a liquid, and its composition will simply be read off the phase diagram like this. If I am told I'm at this point here, I'm in again a single phase region of solid solution, and the composition of that solid, again, I can just read off the phase diagram. If I'm at this point here, however, I'm in a two-phase region. It's a bit more complicated. The average composition can be read off the phase diagram like that. However, there is no single phase that has that composition. What I will actually have is a mixture. I know that I'm at a particular temperature, so I draw a line at constant temperature until I hit a single phase region, which is now at the liquidus. So I will have a liquid, and its composition can be read off like this. I will also have a solid, and I can read its composition off by going at a constant temperature until I hit the solidus, and then going down and reading off the composition of that solid. So at this temperature, a mean composition of 0.5A will give us a solid of composition 0.74A and a liquid of composition 0.23A. Now the next thing we want to know is how much of the system will be a solid and how much of it will be a liquid. To figure that out, we use what we call the lever rule. So what we say is that the proportion of solid will be determined by the lever from the mean to the liquid side, which is from 0.58, the mean composition, to 0.23, the liquid composition. That is to say, the composition at this solid point on the solidus is given by this lever here. Similarly, the composition at the proportion of sample in the liquid phase will be determined by the lever from the mean to the solidus, from 0.74 on the solidus to 0.58 at the mean. This composition here is given by this lever here. To figure out the proportions then, if we want to know how much solid we've got, we take the length of its lever, which was 0.35, and just divide it by the total length, 0.35 plus 0.16, and we get an answer of 0.69. That is the fraction of the sample in the solid phase. That is to say, 69% of the system will be a solid of composition A 0.75, and by subtraction, or we could just work this out, the 31% of the sample will be a liquid of composition 23% A. That phase diagram was based on the assumption that A and B have the same crystal structure type and that they form a continuous solid solution. But what if they don't? What if we just have complete phase separation into A and B in a two-phase region as a solid? Well, as a liquid, they will still be miscible. So this means that they don't completely ignore each other. The fact that they can mix as liquids means that as we move across the phase diagram from pure A, the melting point will drop. And similarly, from pure B, the melting point will also drop. The point at which they meet is called the eutectic point. And from the eutectic point, we will have a straight line in temperature to pure A and pure B. So in the bottom region, we've got a mixture, two-phase region, solid A and solid B. In between there and the liquid, on the A-rich side, we will have a two-phase region of solid A and a liquid. And on the right-hand side, we will have a two-phase region consisting of solid B and a liquid. As phase diagrams become more complicated like this, we have to be careful to ensure that they remain thermodynamically valid. We do this with respect to the condensed phase rule. That says that the number of degrees of freedom of a system is equal to the number of components of the system. In the case of this phase diagram, C equals 2, we have two components, A and B, minus the number of phases in equilibrium, plus 1. So for example, at this point here, I have one phase in equilibrium, which is a liquid. Therefore, I have 2 degrees of freedom. So that means that I could vary the composition without changing the temperature, and I could vary the temperature without changing the composition. Those two parameters are independent, so I have 2 degrees of freedom. At this point here, on the liquidus, I have 2 phases in equilibrium, B and a liquid. 1 degree of freedom. What that means here is that although I can vary both temperature and composition along this line, I have to stay on the line to be at that part of the phase diagram. So that's only 1 degree of freedom because those two are coupled together. Then at this point here, which is the eutectic of the phase diagram, we have a liquid in equilibrium with solid A and solid B, 3 phases, and therefore 0 degrees of freedom for the system. So the eutectic is an invariant point on the phase diagram. We can apply this condensed phase rule to any point on the phase diagram and ensure that it is obeyed, and then we know that this phase diagram is a valid one.